All right, welcome back everyone. So ready and set up now for the last speaker of this morning session. So we have Marek here. It's now with Samsung R&D. You're working on RISC-V architecture and specifically the vector acceleration part, which Henk also showed was one of the ways we can gain this performance efficiency. So floor is yours and please tell us.
Yes, I get the hardest presentation before lunch, so I hope to hold your attention enough. Hello everyone. My name is Marek, and I'm here representing Samsung R&D Institute Poland. Thanks for invitation, Stephen. I'll talk today about RISC-V as the open accelerator platform. I know that we have really broad spectrum of people here, so I'll do a sort of introduction to RISC-V, what is RISC-V, a little bit of history, so that everyone is on the same page. Then I'll talk about the RISC-V Vector Extension, which is one of the I would say most important developments in terms of accelerating software on RISC-V. And then I'll talk about general use of RISC-V as an accelerator platform. So not only sort of ratified upstream things, but what you can do with the architecture with your product, with your acceleration scenario. So first, brief history. RISC-V started in 2010 in UC Berkeley's PARLab, which is Parallel Computing Lab. We have the first ISA manual published in May 2011. So what's really interesting to note is that RISC-V wasn't the main focus of the project back then. It was simply means to an end. They wanted to create some research regarding parallel computing, and they developed RISC-V, which is fifth iteration of RISC architecture at UC Berkeley to do this. Then 2011, first chip tape out. Foundational paper advocating open instruction sets. So it's really interesting to see the moment that the open ISA was advocated, and it basically started the RISC-V momentum, I would say. Then 2015, foundation of RISC-V Foundation, and that's basically the start of more, let's say, organized approach to RISC-V as open ISA. And then 2013, 2018, we have significant DARPA influence. The Aspire Lab, which was succeeding PARLab endeavors within RISC-V, received some DARPA and corporate funding. Here RISC-V was also not the main focus. The main focus was building power efficient embedded computing systems within DARPA. So again, RISC-V was used as a tool basically to enable some research and some development. And 2018-2020, foundation of RISC-V International. So there were some geopolitical concerns about general RISC-V operation throughout the world. So that's the reason why RISC-V Foundation collaborated with the Linux Foundation, and later in 2020 incorporated now known RISC-V International to sort of provide this stable base for RISC-V development in the coming years. So what is RISC-V? I would say it's two things. It's first open ISA with extensions. So the most important thing is that RISC-V is royalty-free and open architecture. So in contrast to some other ISAs, like for example x86 or ARM, which are proprietary and you need to pay a license to use it in your application, RISC-V enables anyone to design, implement, and modify processors. So you can do basically anything you want. You have the open architecture description, and you can either build your own CPU or take some CPU from the market or buy CPU from a vendor and do some stuff with it. And it also includes extending the ISA itself. So you have very big flexibility in terms of what you can do with this architecture. And coming to the flexibility, RISC-V is very modular and extensible. So it was designed like this to have this sort of solid integer processing base, which is RV stands for RISC-V, 32 bits, and I stands for integer base extension, which is like 40, 50 RISC type instructions. And then you have additional extensions. So here I gave example of MAFDC, which is multiply, divide, A for atomic, F for floating point operations, D for double, and C for compressed. But it's not all. We have over 130 ratified extensions. So it's like really big library of things which you can pick and choose depending on your application. And I mean, 130 extensions is nice, but if you're, for example, Linux distribution, what should you target? You are binary, distributing binary files, and you need to know what is running on most of the hardware. So that's where RISC-V profiles come into picture. Quite recently, actually, in October 2024, RVA 23 was ratified, which is really nice because it mandates use of RVV extension. And what profiles basically do is provide the sort of solid base given set of RISC-V ISA extensions, which need to be or are optional in some cases, need to be provided by the hardware to be compliant with, for example, RVA 23. So, for example, in the coming years, we can see some SoCs, for example, application-grade SoCs, which support RVA 23, and then Ubuntu, for example, can run on it. Besides that, the RISC-V International also specifies some non-ISA specifications. That's to sort of coordinate the general direction in the industry so that everyone can collaborate and intermix different IP from different vendors. Yeah, so going to RVV. RVV is one of those instruction set extensions, RV RISC-V, V for vector, first proposed in June 2015, ratified in 2021, so like really long time from inception to ratification, with some additional extensions ratified later on and still ongoing ratification process. RVV is SIMD extension, so similar to x86's like SoC AVX or ARM's Neon and SV, but a little different. Some say it's better. Yeah, it's up to discussion, I guess. It's a little similar to SVE, which has this thing called flexible vector length here in the form of VLAN, which is implementation parameter. So you do not have set in stone the vector register length. It's basically whatever is on the chip is used, and you write software once for RVV, and depending on the hardware architecture, it will run either faster or slower, depending on the VLAN. It is over 180 instructions, so it's largest to date extension in terms of instruction count to RISC-V with some like really nice, highly configurable load store operations. I'll not delve too much into detail because we have not much time, but I included some references, and I'm sure the slides will be shared later, so you can delve much deeper if you're interested in the topic. Yeah, so going forward, what about hardware? Yeah, because we have the specification, and what about the hardware which we can develop on? So RISC-V here comes really nicely in terms of the entire ecosystem. So RISC-V is open ISA, but there are also open source cores which are available on permissive licenses. So you can basically take from GitHub repo, for example, CVA6 and ARA, and build it on your rather large FPGA and experiment with. In fact, that's what I did back in Samsung a few months ago. And here I did sort of categorization in terms of size, small, medium, and big vectors. It's sort of not really, let's say, concrete benchmark, but it gives you sort of overview that there exists a spectrum of different options. So you have very small, embedded, sort of on the edge vectors. You have some sort of compromise one, and you have big vectors like VLANs of 4K with pulp ARA, for example. And those two at the end also support Linux, so you can run your Linux distribution on it and experiment with it. Of course, there are also some closed solutions from commercial vendors, but it's really nice to see that open source ecosystem also provides support for RVV. In regard to like real hardware, so if you don't have $30,000 to buy your FPGA, you can buy, for example, Banana Pi, which is, I would say, the first SoC viable for, the SoC is SpaceMid K1, and Banana Pi uses it, is the first SoC which is viable for development on hardware. We also have DC Roma laptop, so there is a RISC-V laptop with vectors, so you can take your laptop and develop on it your vector code, which is really nice. And it's really nice SoC. It's 8-core VLAN of 256. I included there on the list Canem VK230, but only because it was first. It wasn't really nice target to work with, but it existed, so it's enabled us to do some benchmarks and see how RVV performs compared to Scalar, for example. So going to software, because first we have ISA, second we have hardware, and now what about software? Yeah, because we did all this groundwork, we have hardware, and now we would like to run something on it, right? Regarding general RISC-V situation, there is official or semi-official support from major Linux distros. For example, Ubuntu has like top tier official support. You can go to Ubuntu website and download images for several RISC-V boards. There is also growing support in Debian and Fedora. In Debian, and the next major release will have also official support for RISC-V. And now going back to RVV, regarding development experience. Yeah, so I'm coming from a software team who is developing software for RVV, and we would like to have the tools to do it, right? It's very much possible to develop software under QEMU. There is GDB stub support, so you can have full sort of developer experience. You can go through your code and not resort to prints to debug your code. And there is what is really nice about QEMU. You are able to set VLAN, so you can basically set. Let's say I want to test it on lower end processor. What is the let's say performance, like semi-performance, because you cannot really measure performance on QEMU. It's in fact slower at times than Scalar code, but you can see, for example, instruction count, how many cycles are executed. So you can go from small vectors to big vectors in QEMU and emulate this. And this is really useful also for integration in CI, for example, which I'll talk about later. Regarding general software support, there is really intensive upstream work in open source system libraries, and it includes both community and industry companies, which is really nice to see that RISC-V and extensions are starting to get adopted really intensely by people. I added the notion of extension auto detection, which is one of the more important things in Linux. It's upstreamed from version 6.4, and it enables user to basically query Linux kernel. Hey, do you have vectors? And the kernel says, yeah, I have vectors. So now you can run your RVV optimized code. And if the given CPU doesn't have it, then you can run normal Scalar code. So it's really nice in terms of optional extensions, like RVV was before RV23, because you can compile your binary once for different backends. So you have Scalar, you have RVV, or for some other optimizations, and so you can dynamically see which extensions are supported by your CPU. In terms of toolchain, we have GNU and LLVM. So both support RVV 1.0 and RV23 for the matter fully. There is upstream auto-vectorization support. So basically you write your regular C code, for example, a for loop, and the toolchain automatically transforms your code to vector instructions. And it's already upstream, already released in both GNU and LLVM. Regarding debugger support, it's a little bit iffy, let's say, for now, but it's getting there. There's a lot of momentum in the community and in companies, including Samsung, let's say, to get debugging experience on top tier, like Intel level, let's say, for vectors. And I really recommend those two talks, which are linked down below if you're interested more in the intricacies of, let's say, working on compilers for new architecture, which is RISC-V. It gives very nice in-depth view how is it done? What's the vectorization, auto-vectorization like in compilers, and in general, what is the RISC-V state for example, LLVM? So case study, what do we do at Samsung? As I said, I'm mostly from software team, so we are concerned more about optimization of software for RISC-V. We're part of, Samsung as a whole is one of the premier members of RISE, which is RISC-V Software Ecosystem Project. It's sort of sister project to RISC-V International, which is concerned mostly about bringing first-class support to software for RISC-V, and it's concerned with open source libraries and applications. And we're taking part in several working groups, system libraries, toolchains, language support. And my team in particular is concerned with RVV optimization. As I said, I did some experiments with virtual RVV capable targets. I was running Pulp ARA on AWS FPGAs, so it was really interesting experiment. So you can see my talk from OrConf this year. Also, what I told at OrConf was CI setup, because when you're developing your optimizations and you want to upstream it, the projects, well, they don't necessarily have the hardware, for example, to test it, or don't have the expertise to run the CI and QEMU, for example. So what's really important for companies and people who want to upstream their optimizations to also provide support in form of, for example, CI. So in case of Pixman, for example, we extended their CI pipeline to include RISC-V target, and it was before merging our RVV support. So first came the CI. They were able to see everything, all the tests pass and how it performs. And then we pushed the merge requests for RVV backend, which also passed the CI. I mean, at first it didn't, which passed the test for CI, I guess. So yeah, we're working on adding RVV support to system libraries, and it's mostly hand optimizing RVV code, RVV assembly, in some very specific cases where auto-vectorization isn't suitable. Yeah, and the last point, what we do at Samsung is Tizen OS. So I'm not sure if who is familiar with Tizen. Tizen is operating system which is used in some appliances at Samsung, and Samsung will use RISC-V as the platform for Tizen in future products. So we basically provide bring up support for Tizen, including some support for product divisions. So let's talk about a few case studies for RISC-V as an acceleration platform. So I introduced RISC-V. I told about current, let's say, top thing, which is RVV. And what about RISC-V as a whole ecosystem? What's possible to do? I was thinking what to do here, and I thought, yeah, let's show a few examples what people in industry and academia did with RISC-V as a platform. So first example is VRP, a variable extended precision accelerator for scientific computing applications. It's a really interesting thing because, as I said, RISC-V, you can take the entire ecosystem and extend it with your own ISA extension. So here, the use case was for some scientific research where they really needed extended precision of floating points numbers for some like iterative algorithms. So they developed their own ISA extension, which was tightly integrated with the RISC-V core. which enables you as a developer to use single toolchain, single ecosystem of tools to integrate your own extension and accelerate your application. Second example is BSC. BSC is Barcelona Supercomputing Center. They are developing like really huge HPC class CPUs, and they are experimenting currently with RISC-V for their next generation of HPC supercomputing chips. And what's really interesting is that they're also adopting RVV as one of the cornerstones of their chips. They have their own implementation of RVV, which is like really large APC scale. And I think they also open sourced it. I'm not 100% sure. They also have some really interesting tools for prototyping on FPGAs for really large designs which span multiple FPGAs. And I would say it's really interesting talk to watch to get to know this sort of higher end of what's possible with RISC-V. Then we go to the more low-level edge sort of part, which is neuromorphic acceleration. So a PULP project within ETH Zurich they used their own CPU IP, which is Snitch, and then they extended it with some SNN optimized extensions. So as I said before, you take the entire ecosystem and you extend it with your own secret sauce and enable acceleration and, for example, better energy efficiency for your specific application. And yeah, we have Accelera, which would be bad to omit. I would say, regardless if we had a guest from Accelera today, because it's really nice example to see a company which basically looks around what's available. Yeah, here is RISC-V. Here's the entire ecosystem, and we can use it. We can grab whatever we want. We can prototype with open source cores. Then we can go to vendor and buy their IP, and we can extend it with our own, as I said, secret sauce and sell it as a product. Yeah, so we're taking this entire ecosystem, the security things, the cores, the tool chains, yeah, and then we package it into our product and sell it. Yes, I think this talk which I linked goes much more in detail what is the hardware architecture and how RISC-V is used, but yeah, it's a really nice example. So what's on the horizon? I would say there are multiple directions. Everyone talks about AI, ML, so that's the central things, right? And I would say in case of RISC-V, it's a really good case because you have, as I said multiple times, the solid base, and then you can extend it with your own, I think, be it for LLMs, for SNNs, whatever NNs you have, and build your application on top of this ecosystem. There's interesting development in this direction in case of like general standardization of ISA in matrix extensions. There are two approaches, IME and AME. I will not delve too much into detail because we don't have that much time, but it's really interesting to see the development of the future next generation, let's say RVV plus, let's say, acceleration in RISC-V ecosystem in more standardized way. So not really your secret sauce, but this will come in standard CPUs in, let's say, 10 years probably. And third thing, scale of adoption. This is a keynote from Calista Redmond from RISC-V International, and she claims, of course, we need to take it with a pinch of salt, of course, that by 2030, RISC-V will be shipped in 30% of SoCs. So it's really ambitious, but I would say by looking at the appeal of RISC-V for companies, that you can basically tap into a really large ecosystem and do some additional things on top of it. I would say it's not far from the truth. We'll see, of course, in a few years, but it's really interesting to see that RISC-V is gaining momentum, especially in AI, ML, accelerator type of applications. And I added on the bottom here a Core 5 extension interface, which is really interesting development if you're developing your own custom accelerator. This is proposed, actually already ratified extension interface, which basically standardizes the way of communication between a CPU and your custom accelerator. So for example, CV32 and CVA6 already have it. So let's say you created your custom accelerator, you tested it with CV32, but then you say, yeah, I think I need a bigger core, for example, to do some more application level stuff. Then you can simply, I mean, that's the idea, exchange CV32 with CVA6. And I can see there's a lot of cores which are starting to implement CVX in future. So it's really interesting. So summary, what RISC-V offers to you in terms of acceleration platform? First, flexibility, and it's twofold flexibility. First, it's the freedom to customize the feature set in form of picking and choosing your own set of instruction extensions, or taking the solid base of, for example, RISC-V profiles and extending it with your custom either ISA extension or your like coprocessor, but tightly coupled with the processor. Then the second part of flexibility is scalability. So RISC-V sees applications in really broad range. So from embedded, like low-level, low-area applications, up to like really huge AI, HPC workloads. And you can choose whatever part of the spectrum you want, you target, and pick some open source cores or from vendors. Second is the ecosystem. I've talked about it multiple times. RISC-V offers really vibrant ecosystem of both hardware and software. So we have the ISA base, which is coordinated by RISC-V International, but then you have really vibrant community of companies and academia, which create cores, IP, which you can use, but also in form of open source software, which either is used to build, for example, tool chains and enablement of retargeting, for example, in tool chains, and software which runs on standard instructions, standard CPUs. And that leads us to the third thing, community. So everything what I said is created in really broad open community of companies, academia, individuals, and I would say it's sort of taking the good of open source software and extending it to the hardware to create sort of open hardware ideal, which is really nice to see. It's gaining some momentum, and we can see really nice cooperation, global cooperation between even competitors doing something to create this beautiful ecosystem. Yeah, so thank you very much for your attention. If you have any questions, probably during the lunch, right? Everyone's hungry. Yeah, thank you very much.